Hey guys, welcome to chapter 6. So in chapter 6, we're going to continue talking about chemical bonding. But what we're going to do here is step away, from the Lewis structure and step back into this idea of quantum mechanics. So the Lewis structure gives us a really good indication of how things are bonded together, but it doesn't give us a good picture of reality. So as we know that electrons are not dots, so they do not behave like those little dots that we've been drawing. So that's one of the major limitations of the Lewis structures. It's not reality. Okay. So just continuing with this thought, here's some problems that we run into with this Lewis theory. So the Lewis theory generally predicts the trends and properties, but does not give good numerical predictions. So if we were trying to predict bond length and bond strength, if we were trying to predict bond angles, for example, the Lewis theory just doesn't give us these kind of numerical predictions that we as scientists really do enjoy those numbers. It also gives us good first approximation, but it cannot give us the actual angle. So it can tell us that, yes, probably tetrahedral-ish, but it won't tell if it's 109.5 degrees or 104.5 degrees. So it doesn't give us, again, those actual numbers, those actual angles. Just a good approximation. So Lewis structure is a good qualitative theory. And actually, once we discovered quantum mechanics, we found that the Lewis theory was actually very, very good. But it's a good qualitative. What we're about to study now is going to give us more of a quantitative look. So we're going to study something called the valence bond theory. So the valence bond theory, of course, focuses on valence electrons, no surprise there. But it's going to say that the valence electrons of atoms reside in those quantum mechanical orbitals. So we're going to go back to talking about S's and P's and D's and F's. We're going to look at what the spheres and the double lobes and the four lobes look like in 3 dimensions. So we're going back to all of that in quantum mechanics and tying it in with the Lewis theory. A chemical bond will result from 2 overlapping half-filled atomic orbitals. So if we think back to orbital diagrams, remember orbital diagrams were our boxes. If we think back to those boxes, in the boxes, it had 1 electron in it versus 2 electrons in it. So 1 electron would be a half-filled orbital, and that would give us an opportunity for bonding with somebody else that was half-filled. So those 2 orbitals overlap, and we would get a chemical bond. The geometry of the overlapping orbitals determines the shape. So this is where we'll see that the valence bond theory and the Lewis theory do match up very, very nicely. So we'll see the same sort of geometries that we've already studied. And here's kind of a new piece here. So the orbitals can be the standard SPDF that we've seen. But we're also going to talk about something called hybrid orbitals. So these hybrid orbitals are going to be a combination of 1 or 2 or 3 of the other orbitals to make this hybrid orbital, which is just going to increase our stability and increase our availability for making bonds. So we'll talk about hybrid orbitals. All right, so let's take a look at an example. So if we look at H2S, here's what we see from an orbital diagram perspective. So we've got, let me get my pointer. All right, so up here we've got 2 atoms of hydrogen. How many valence electrons does hydrogen have? Hydrogen has 1 valence electron. So you see that right here. And that 1 valence electron is in the 1s orbital. So that would be a half-filled orbital there. We've got another hydrogen atom. It also has 1 valence electron in that 1s. So here's 2 opportunities for bonding. If we look at sulfur, so how many valence electrons does sulfur have? Sulfur has 6 valence electrons. It's in 16 or 6A. So it's got 6 valence electrons. 2 of those 6 are in the 3s orbital, and that one is full. The last 4 are in the 3p orbital. So 1, 2, 3, 4. So according to the valence bond theory, a chemical bond results from the overlap of 2 half-filled orbitals. So if I wanted to make a bond between hydrogen and sulfur, this hydrogen could bond with this half-filled p orbital. So in other words, this sphere can overlap with this lobe, double lobe, and that would be 1 bond. And this hydrogen can overlap with this other p. Sorry guys, I have the yawns. This hydrogen can overlap with this other p, and that would be another bond. So half-filled sphere, half-filled double lobe, they overlap and create a bond. Okay. So here's what we see from a quantum mechanical perspective. So when I first put this on the screen, it probably looks like a bunch of balloons all tied together. But throughout this chapter, we're going to start training our eyes to see exactly what's going on here. So the first thing I'm going to talk about are these hydrogens. So as we said, the valence electron is in the 1s orbital, and s orbital is a sphere. So here's one of those hydrogens. Here's the other hydrogen. For sulfur, if we're looking at just the valence electrons, so yeah, there's more going on inside of here with the core electrons, but to try to keep things simple and straightforward, we're just looking at the valence orbitals. So for sulfur, we should see an s orbital that has 2 electrons in it, and that's exactly what we see here in the middle. We should see a p orbital. So remember, a p orbital is the double lobes. We've got one going up and down, one going left and right, one coming out of the screen and going back into the screen. So that's exactly what we see here. Here's one going up and down. Here's one going back into the screen, coming out at us. And here's one going right to left, okay? So we see those 3 p orbitals. One of the p orbitals was already full, so it had 2 electrons in it, and that must have been the up and down orbital here. So up and down orbital, we've got 2 electrons in there. These guys were half filled, so the left and the right, and the coming out at us, going back into the screen, were half filled. They overlapped with a hydrogen atom to create a bond. So this is the overlap right here. This would be where they share electrons. So this would be a chemical bond right here. And this would be the other chemical bond right here. Again, the overlap of 2 orbitals. So that's taking the valence bond theory approach and looking at this from a quantum mechanic perspective. Okay. So let's think about CH4, methane. We've seen CH4 before. We know that it makes a molecule that looks something like this. And please forgive me for my drawings. I don't have my pen right now. I'm trying to use a mouse. So forgive me for how messy this is. But this is what methane looks like. Draw. There we go. All right. So we got carbon in the middle. 1, 2, 3, 4 hydrogens. Okay. So we know this is what methane looks like. Just want to make this a little prettier. There we go. Okay. So if we think about the geometry of methane, we see that it has 4 bonding groups. We know that's going to be a tetrahedral molecule. So that's what the Lewis theory predicts. And when we actually go in and reach inside of that molecule, what we find is that it is in fact a tetrahedral molecule, that carbon does make 4 bonds, and those bond angles are 109.5. Okay? So if that's what the Lewis theory predicts, this valence bond theory should help us to understand where those bonds come from, right? So the valence bond theory should follow suit with the Lewis bond theory. But looking at the orbital diagrams, we see that there's something going on here, okay? So there must be some sort of wrinkle that we haven't talked about yet. According to the valence bond theory, a bond can be formed by the overlap of 2 half-filled orbitals, okay? So if we've got CH4 here, right? We know each of the hydrogens has 1 valence electron, and they are half-filled orbitals. So we've got 4 hydrogens that are ready to make bonds. But if we look at the valence electrons for carbon, we see a little problem here, right? So carbon has 4 valence electrons. 2 of those electrons are in the 2s orbital. 2 of them are in the 2p orbital. Looking at this orbital diagram, how many electrons are available for bonding according to the valence bond theory? Yeah, the only 2 that are available for bonding are this guy and this guy. So half-filled orbitals is what creates a bond. And this looks like we could only form 2 bonds with carbon. So how did we get 4 bonds? Well, there must be something else going on here, okay? So if we just keep it at face value, if we just keep it the way it is, the valence bond theory predicts that we can only make 2 bonds with this carbon atom, and that those bond angles would be 90 degrees. But when we actually study CH4, we actually study this molecule, observed reality looks something like this. It's a tetrahedral molecule with 4 bonds. So how do we go from an orbital diagram that looks like this to a model or a molecule that looks like this? Well, there's some other things going on behind the scenes here. So the 2 things that we have to talk about to help us understand how we actually get this molecule is we have to talk about hybridization. And then we also have to talk about the fact that carbon will expend a little bit of energy to promote this electron to this open or empty orbital. So if I take this electron and I put it over here in this orbital, now I have 4 half-filled orbitals, 4 opportunities for bonding. So by paying a little bit of money up front to move that electron, carbon gets a huge payoff in the end by being able to make 4 bonds. So that's the 2 things that are going on here. 1, he's going to promote that electron. And 2, we've got some hybridization because all of these bonds are actually identical. They're exactly the same. So let's talk about orbital hybridization. So orbital hybridization is the orbitals in a molecule. So once we put this all together, are not necessarily the same as the orbitals in the atom. So in carbon, for example, we had s and p orbitals, just standard s and p orbitals. When carbon goes or gets ready to make a bond with hydrogen, he's going to hybridize or smash together all of those orbitals to make what are called hybrid orbitals. So the hybrid orbitals are in our molecule, standard orbitals are in our atom. Okay. This is a mathematical procedure. So remember that these orbitals are mathematical solutions to a wave equation, right? They all came from math. So when we combine these orbitals together, when we smash them all together, it's actually a mathematical process to combine those waves. So here's a picture of what a hybrid orbital looks like. Here's a picture of what a standard orbital looks like. Okay. So the electrons are still localized within that hybrid orbital. The hybrid orbital just has a new shape. So let's say we had an electron over here in this lobe. When we hybridize the orbital, that electron is still there. This lobe just has a slightly different shape. So greater probability on this side, lesser probability on this side. So it's just a new shape, but the electrons are still localized in there. Okay. What these hybrid orbitals offer us is a maximization of overlap. So this strengthens the bond. So not only do we get this larger area here for that overlap to occur, we also, by hybridizing, get the opportunity to make 4 bonds instead of 2 or 3. So by maximizing the number of orbitals, we maximize the amount of bonds. And by maximizing the size of this orbital, we maximize the amount of overlap. We strengthen that bond. So again, everything we do in chemistry is always in the name of stability or strength. Okay. So this is not a free lunch. So we do have to expend a little bit of energy to hybridize these orbitals. We do have to expend a little bit of energy to promote these electrons. But the payoff for that is a huge, huge payoff. Okay. So more bonds, maximized bonds, will give us more energy that comes out of that, more stability, more strength in those bonds. So if we get huge payoffs, we're more likely to do whatever it is that caused us to get that payout. So those more bonds gives us a greater tendency to hybridize. So hybridization just stacks the deck in our favor. It's really what it does. Okay. So real quick, what I want to do before we move forward is I want to talk about how we get this large lobe and little lobe. So remember that these are waves, right? And when we talked about waves, one of the properties we talked about was constructive and destructive interference. So when these orbitals come together, when these waves come together, there's going to be a region where they come together in phase, and that's going to be constructive, things get bigger. And there's going to be an area where they come together out of phase, and that's going to be destructive, things get smaller. So if we look at smashing together this S, P, 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 what we'll see is we'll call the black area out of phase. We'll call these white areas in phase. So when we smash this all together, here's where the waves came together in phase, and that portion got bigger. Here's where the waves came together out of phase, and that portion got smaller. So that's how we get this lopsided hybrid orbital. It just goes back to the characteristics of waves that we've already talked about. All right, so just some general truths about hybridization before we dive in and look at specific examples. So the number of standard orbitals that we add together is going to equal the number of hybrid orbitals that we get out on the other side. So another way to say that is if I smash together 4 standard orbitals, I'm going to get 4 hybrid orbitals out on the other side. If I smash together 2 standard orbitals, I'm going to get 2 hybrid orbitals on the other side. So whatever I put in is what I'm going to get out. Put 3 in, get 3 out. Put 4 in, get 4 out. So the standard orbitals added together equals the number of hybrid. Okay. So here's a picture of this first hybridization that we actually did and we're going to talk about. So what it does is it's going to smash together that 2s orbital for carbon with the 2p orbitals. So one of the 2 s's, 3 of the 2 p's. So I put 4 things in, magical hybridization happens, and I get 4 things out. The 4 hybrid orbitals that I get out are all identical now. So we've got 4 identical orbitals that came out on the other side. I really like how this graphic is done. This is from your textbook for 2 reasons. So one, when you mix blue and red together, what color do you get? You get purple. So I think that does a good job of showing us that we put 4 things together and get 4 identical things out on the other side. Okay, we mix some colors and we get purple. The other thing I like about this is it does a really good job of the energy of these hybrid orbitals. So if I mix low energy S with high energy P, the hybrid orbitals that come out the other side are going to be somewhere in the middle of that energy-wise, right? So low energy plus high energy is going to give us something in the middle. So these hybrid orbitals are going to be greater in energy than S, but they're going to be lower in energy than P. So again, lower energy, more stability. So that's another reason to hybridize. And then the last thing I want to point out here is here we've got 2 unpaired electrons. So if we did not hybridize, carbon could only make 2 bonds. But once we smash all of this together, now we get our 4 hybrid orbitals. All of them are half filled. Now we have 4 opportunities for overlap. So this gives carbon twice as many opportunities to bond now. So I've alluded to this, but the combination of standard orbitals dictates the shape and energy of the hybrid. So I put 4 in, I get 4 out, and what we'll see in just a minute is that's tetrahedral, okay? I also talked about the energy, so it dictates the energy. So if I put 3 high energy p orbitals in, these guys coming out the other side are going to be a little bit higher in energy. But if I can leave out one of the p orbitals, which we'll do much later, this will be a little bit lower. And if I can leave out 2 p orbitals, this would be even lower. So what you put in is going to dictate what comes out the other side. Okay. So here's the hybridization process in pictures. So instead of just having lines or boxes for orbital diagrams, now we're going to look at the actual 3-dimensional models, the actual orbitals. So we are going to hybridize an s orbital, which is a sphere, and 3 of the p orbitals. So remember, one of them's up and down, one of them's left and right, one of them's coming out of the screen, going back into the screen. So we're going to take all 4 of these guys. We are going to smash them all together, and we're going to get 4 identical orbitals out. Put 4 in, get 4 out. So these are the 4 orbitals that we get out. Notice they're all identical. Big lobe, little lobe, big lobe, little lobe, big lobe, little lobe. Okay? When these hybrid orbitals come together, so when they superimpose or stack on each other, they're going to do so in a very particular manner. So this should start to look familiar. So they're all going to face their little lobes in, right, and face their big lobes out. So they want to maximize overlap, so they're going to put the big lobe on the outside. Okay. When they do that, they're going to try to get these lobes as far away from each other as they can possibly get. So to get those big lobes as far away as they can possibly get, it's going to come together in a tetrahedral molecule. So they want to put 109.5 degrees between each of these lobes. So all of these hybrid orbitals have the same energy. all of these hybrid orbitals are going to dictate the geometry of the central atom, that tetrahedral geometry. And we'll see that tetrahedral geometry and then the types of hybridization are very much related. Okay. So an atom with 4 electron groups around it has tetrahedral geometry. The name of this hybridization is called sp3. So this is one of the most logical names in all of chemistry. So how did we get this sp3 hybridization? How did we get this name? We got it from telling the viewer exactly what we put in. So I put in 1 s orbital, I put in 3 p orbitals, and I get sp3 hybridization. So it's just literally telling the viewer what you put in to get that. Okay, so sp3 hybridization. Atoms use the hybrid orbitals for all bonds and lone pairs. So here in our carbon example, we see those hybrid orbitals. So hybrid orbitals are shown in purple here. And in this picture, all of those hybrid orbitals have overlapped with the hydrogens to create those 4 hydrogen bonds that we saw. So here's hybrid orbital overlapped with hydrogen. Hybrid orbital overlapped with hydrogen. Hybrid orbital overlapped with hydrogen, hybrid, hydrogen. So there's our 4 bonds. The hybrid orbitals don't necessarily have to bond, so they can house lone pairs. So here we see our ammonia example, our NH4. Again, I'm going to try to do my best to draw this. So NH4, according to the Lewis theory, look like this. Excuse me, NH3. And we had a lone pair up here, right? Okay. So again, when we did the Lewis theory here, we said that that was a tetrahedral molecule, right? We got 4 lone pairs. So we're predicting 109.5-ish for the bond angle. This nitrogen will hybridize its orbitals. So it will do the same kind of hybridization as carbon, to try to maximize its bonds. So it'll do that sp3 hybridization. And then we'll see those hybrid orbitals here. So here's 1, here's 2, here's 3, here's 4. So we see those 4 hybrid orbitals. The difference here is that nitrogen only makes 3 bonds. So here's overlapped with hydrogen 1, overlapped with hydrogen 2, overlapped with hydrogen 3. So those are those 3 hydrogen bonds. And the last hybrid orbital is housing that lone pair of electrons, okay? So even though it hybridizes, it doesn't necessarily have to make a bond. It can just simply house lone pairs. Okay. So not everybody does this sp3 hybridization. There are going to be some instances where we don't necessarily need 4 hybrid orbitals. What if we just need 3 hybrid orbitals? Okay. So if we need 3 hybrid orbitals out on the other side, that means we just need to put 3 standard orbitals in. So we would put 2s, 2p, 2p. So 3 orbitals in, I get 3 hybrid orbitals out. And that leaves one of our P's to be a standard or an unhybridized P. This is important for multiple bonds, which we'll see in just a minute. Why would I want to leave a p orbital out if I could? Well, if I leave this p orbital out, that's going to drop the energy for these hybrid orbitals a little bit, right? Because remember, these guys are higher in energy. So if I can leave one of them out and still accomplish what I need to accomplish, that's going to cause my hybrid orbitals to be a little bit more stable, a little bit lower in energy. Okay. Here's a picture of what that looks like. So I put in an S, I put in 2 of the P's. So I put in 3 things, I get 3 things out. When these guys line up, they're going to do the same thing, try to get the maximum bond angle between the 3 fat sides. So the geometry that we'll see here is trigonal planar. That unhybridized p orbital, this is going to be important a little bit later. That unhybridized p orbital is still there. So if I could draw that into this picture here, that unhybridized p orbital would be perpendicular to this. So this is flat on the paper. That unhybridized p orbital would be going down into the paper and coming straight out at you, like pointing at you. So that unhybridized p orbital is still there, and it's perpendicular to these other orbitals. Okay. So we looked at putting looked at putting 4 orbitals in, getting 4 hybrid out. We looked at putting 3 orbitals in, getting 3 hybrid out. What do you think is next? Yeah, putting 2 orbitals in, getting 2 hybrid out. So here I'm putting in a 2s and a 2p. So 1, 2 orbitals in. I get 1, 2 hybrid orbitals out. And those other 2 p's stay unhybridized. Okay, so 2 in, 2 out. Looking at the picture here, so I have 1, 2 standard orbitals in. I have 1, 2 hybrid orbitals out. Again, the fat sides are going to want to get the largest bond angle between them. We'll overlap our smaller ends, and we get a linear structure here, a linear. Central atoms are hybridized based on VSEPR electron geometry. So what this statement is telling us is that if you are seeing a pattern between hybridization and the geometry that we talked about, you're not crazy, you're absolutely correct. So SP hybridization will always be linear. SP2 hybridization will always be trigonal planar, and SP3 hybridization will always be tetrahedral. So there certainly is a connection between hybridization and electron geometry. The key here is electron geometry, okay? So we're not talking molecular geometry. We're taking electrons into account. So electron geometry and hybridization are connected. All right, so that is where I'm going to end our discussion on hybridized orbitals. I'm going to do another video from chapter 2, which expands upon this idea a little bit more. So we'll talk about the expanded octets, and we'll also talk about sigma and pi bonds. But this was just an introduction to your hybridization. Hope you guys found this helpful.